Hello students, in this video, we will learn how highly reactive metals are extracted using electrolytic reduction, and how impure metals are refined using electrolytic refining. Why can't we extract sodium or aluminium by heating with carbon? Why are some metals still impure even after extraction? These problems lead us to use special methods, electrolytic reduction for very reactive metals, and electrolytic refining to get pure metals for industries. Electrolytic reduction means extraction of metal from its molten compound by passing electric current. This method works for metals high up in the reactivity series like sodium, potassium, calcium, magnesium, and aluminium. Let's set up a basic electrolysis experiment. In this setup, positive metal cations and negative non-metal anions are involved. Let's see the chemical equations and reactions. For sodium chloride, at cathode, Na plus E creates sodium metal deposits. At the anode, 2Cl turns into Cl gas. Now, let's look at aluminium extraction from alumina via the Hall-Héroult process. At the cathode, Al cubed plus 3E produces molten aluminium. The anode reaction involves oxide ions, where oxygen evolves and reacts with carbon. Cryolite plays a crucial role. It lowers the melting point of alumina and increases conductivity. Electrolytic reduction has a few pros and cons to consider. Advantages include extraction of very reactive metals and high purity. Disadvantages include high costs and energy consumption. Key facts include melting point of salts and role of electrodes. Remember to focus on electrodes, half reactions, and the reasons why carbon reduction fails for some metals. Now, let's dive into electrolytic refining. Refining is necessary because impurities can affect conductivity, strength, and corrosion properties. Electrolytic refining uses an impure metal as the anode and a thin strip of pure metal as the cathode. The electrolyte, often an acidified copper sulfate solution, facilitates the transfer of pure metal. As current flows, soluble impurities dissolve while metal ions migrate and deposit on the cathode. Insoluble impurities fall as anode mud beneath the anode. Let's review the chemical reactions involved in this process. At the anode, Cu turns into Cu squared plus 2 electrons. At the cathode, Cu squared plus 2 electrons creates copper. Commonly refined metals include copper, silver, gold, tin, and nickel. For example, pure copper is essential for electrical wiring. Jewelry often uses pure silver and gold. One common mistake students make is confusing anode and cathode roles. Another mistake is forgetting the importance of anode mud. Remembering to include balanced equations is key for scoring well. Diagram labeling can be a game changer in board exams. Now let's compare electrolytic reduction and refining. Electrolytic reduction extracts metals from molten salts. Refining purifies extracted metals. Compare ore states. Molten compound for reduction, impure solids for refining. For metals, electrolytic reduction for highly reactive metals, refining for metals that need purification. The anode material differs, often inert in reduction, impure in refining. Cathodes also differ, inert in reduction versus a pure metal strip in refining. Real-world examples include aluminium extraction and copper refining. Now let's discuss common CBSE exam questions. Describe the electrolytic refining of copper with reactions in a diagram. Explain why aluminium oxide is dissolved in cryolite during extraction. Discuss why aluminium can't be extracted by heating with carbon. Addressing half reactions. Balance these equations. Explain the use of anode mud and the differences in soluble versus insoluble impurities. As we wrap up, revisit the key points on electrolytic reduction and refining. Mastering these topics helps you score well in chemistry. They appear often. If this video helped you, hit like and subscribe, share with friends, and comment below any doubts. Check out other videos on CBSE Class 10 Science.